We're working our way towards an important and useful but kind of esoteric concept, and to get there we're going to talk about the parable of two surveyors. Katya is hired to create a survey of 4 local hills, A, B, C, and D. She decides to report her results, because she's a little strange, in terms of the potential energy climbing each one from sea level, which of course would just be equal to the gravitational potential energy she has at the top of each. So she makes her measurements, and she says at the top of hill A, she has 29.6 kilojoules, and at the top of summit C, she has 40.4, etc. She produces the following map for her clients, who are probably not that happy with her, but that doesn't really matter. And you can see she has plotted basically each hill on its GPA. And so you can see the peak, and you see that B is more than A, and C is more than A, and D is more, right, but B is more than C, and so on. That's her little map. But her much bigger brother Leopold says this is ludicrous, because on the top of hill A, his gravitational potential is not 29.3, but is really 44.4 kilojoules. So her map is too low. What would his map look like? Think about it for a sec. Well, of course, since the gravitational potential energy is proportional to mass, for Leo to have 50% more GP on hill A, he must be 50% more massive than Katya is. His mass is 1.5 her mass. But that would mean that all of his GPs are 50% larger. So his map would look like this. And you might say, that looks kind of suspicious, or at least somewhat familiar. Side by side. So we have Katya's here, and we have Leopold's here, and we see those maps look very similar. They're almost the same thing. It's even better and even easier to see if we put them on the same graph, and we can see that basically they look the same. There's something that those shapes are not distinct. There's something that's the same between the two graphs, even though the values are wildly different. Why do they get the same shape even though they have very different masses? Because the values differ due to the masses, but the energy is also dependent on the shape of the land. So here's a picture of the actual place that they were trying to survey. We have the hills, and we see, of course, that their peaks on their maps are the peaks on these maps, and those peaks were determined by the heights of the actual peak from sea level. That is, the ratio of the gravitational energy here to the gravitational energy here, for instance, doesn't depend on who you're asking. That Leo's energy at B over Leo's energy at A would be the same as Kate's energy at B, Katya's energy at B over Katya's energy at A. The ratio is produced not by the surveyor, but by the shape of the Earth and the gravitational strength the Earth exists. All right, these are the two things that are giving us these two shapes. We could, if we were interested, define some quantity. We're going to symbolize it with V sub g. Hopefully those reasons will become clear later when we talk about the potential in electricity. But take the V just as a V. We could define that quantity as the potential energy they find over the mass. So each surveyor measures the gravitational energy that they would have going that high, maybe by figuring out how many calories they burn in climbing the hill, and then divides by their own mass. And the key thing is that different surveyors would report different mu sub g's, right? Because their energies would all be different. But they would all agree on V sub g. They would all be the same. That's a property. Whatever this V sub g is, it's a property of the environment, not of the individual surveyor. It's the lay of the land. As an aside, we see that's literally true, right? We can say, if we take that formula and we actually put in, the height, the energy at height h is mgh, then we see that the masses, of course, cloak, right? The masses go away. That this fraction is 1, so we don't write it anymore. And in fact, this weird V sub g is just g times h. And therefore, it doesn't matter who you ask, because they all have the same g and they all have the same h. Right? This weird thing is a product of the Earth's gravitational influence and the position of the surveyor. But of course, since g is the same everywhere, the surveyors would really just report the height. They wouldn't say, here's this map and it's in terms of gh. They would just give you a map in terms of h, which is what you hire surveyors for. Obviously, this has been a contrived example. But in cases where g happened not to be constant, for instance, if you talked about things moving very distant from the Earth, or with multiple planets, and you're talking about surveying the solar system, then we'd want both factors there. We'd actually have to be a little bit more complicated. If g varies, this would become some function of where the mass is in our system. For gravity near the Earth, all of this has been silly. The height is sufficient, which is why you've never heard of this weird thing called S of g. But for electric fields, the same concept can be very useful. This thing, r v sub g here, what we just call v sub g, gets a weird name. It would be called the gravitational potential. What we're really interested in, of course, is the electric potential, and we'll talk more in the next one about what is this potential and what's going on. Where is it coming from? How do we define it?